All right, thank you for the introduction, and thank you for the opportunity to give a talk here. It's a very interesting workshop. So today I'm going to be talking about recent work that we put out on the archive. And this is a work that's been done in the atom array group at Harvard, in the Lucan group. And it is, if you recognize some of these words, due to Tron's talk, it's not a coincidence. So it has several parallels to what Tron was discussing, but also several, I think, complementary aspects. So thanks, Tron, for doing some of the introduction for me. Right, so the platform is pretty different. So instead of this superconducting qubit platform, we work with the so-called Rydberg atom arrays, and these are systems which are built on the idea that you can hold on to atoms using light. And specifically, if you take a laser beam and you focus it down pretty strongly, you get these so-called optical tweezers. And we can hold single atoms with these optical tweezers, and we can do that for many, many atoms. So here you're seeing an array of 400 atoms, and this is a single shot, it's not an average image. And each of these circles is a single rubidium-87 atoms, and they're a few micrometers apart. Because the trapping is based on these laser beams, and we know how to control these extremely well using all kinds of optical tools, then we can create whatever geometry that comes to mind. Whether it's these regular lattices or even these disordered lattices, you can create deterministically. So essentially, any geometry that you'd like up to some resolution constraints. And now once you have these neat, nice ordered lattices, you want to do some quantum science with them, so you want to get them to interact. And the way we do that in this system is by exciting the electrons to a highly excited state known as the Rydberg state. And so I mentioned that the atoms here are a few micrometers away, so several orders of magnitude further away than they would be in a condensed matter system. So their kind of native interaction, the ground state is extremely weak. But once you excite them to this highly excited state with a principal quantum number, people typically use anywhere in the range of this like 40 to 100 or so. The wave function grows pretty significantly, so it has an extent of a few hundreds of nanometers typically. And moreover, the dipole moment grows, and therefore the induced dipole-dipole interaction, the van der Waals interaction, grows extremely quickly with the principal quantum number. So what you have is you have the situation where if you have two atoms far apart, essentially they don't interact because this interaction falls off pretty quickly. But if you put them close together, the doubly excited state is so high in energy due to this extremely strong interaction that essentially it's energetically forbidden. And we call this the Rydberg blockade. So essentially, under some radius, you can think of the interaction as being so strong that these doubly excited states are almost removed from the Hilbert space. Right. So one could do many things with these types of systems, and there's this whole world of digital quantum processing with these atom arrays, which I will not discuss today. But a lot of the things that, a lot of other things can be done using this analog modality. We essentially turn on, you order these atoms in one of these lattices, and you turn on the interactions. You can get all kinds of really neat and cool physics. This is just some examples from the last few years, exploring quantum phases of matter in 2D, looking at non-equilibrium dynamics, and specifically these many-body quantum scars and their stabilization, trying to solve combinatorial optimization problems. This is with Eddie and very much inspired by his work. And looking at exotic states of matter, spin liquids, topological states of matter. And so these systems are pretty nifty. You can get these arbitrary geometries which are highly programmable. You have high fidelity operations, which I'll mention in a few. And you get these abundant and identical qubits. So we typically work with systems of hundreds of qubits, but recently people have already shown arrays of several thousands of atoms, for instance, at Caltech. And we get this kind of individual atom readout, and something new that we've added recently is also an individual atom control in the context of these analog experiments, which we'll use in this project. And Tron has also shown nicely this analog-digital approach. So these analog systems are very powerful, but they can also be used in conjunction with some digital approaches. So there's a lot of opportunities still working with these analog systems. looking at both equilibrium and dynamical behavior of quantum many-body systems, and people have also used them to prepare highly entangled states, for instance, as resources for quantum metrology. In the context of this talk, I'll focus on something which is related to these two parts. So looking at quantum phases of matter and how they relate to dynamics out of equilibrium. And also not only the phases of matter, but the phase transitions and how they relate to dynamics. So what we have in the system is we have this ordered array. And what we've explored before, as I mentioned, is these phases of matter. So in this work, what we did is we took this ordered lattice, turned on the Hamiltonian, and we have this type of Hamiltonian. So you turn on a laser, which couples the ground state to the excited state. And this laser has some detuning. And you have the interaction coming from the Rydberg physics I described before. So you take this Hamiltonian, you evolve the system over time, varying these parameters. And here we're choosing the Rydberg blockade to be nearest neighbor. So you have essentially extremely strong nearest neighbor interactions that fall off pretty quickly with distance. And once you do this, you can vary these parameters, the omega and the delta of your laser, to go from a situation where the ground state is kind of trivial, what we call the disordered state, where all the atoms are in the ground state. You go through a phase transition into quite a different state. So here the system wants to kind of like maximize the amount of Rydberg excitations, but it's subject to this blockade constraint. So nearest neighbors cannot be simultaneously excited because of the energy cost. Great. So what you get, as you see here, is this kind of antiferromagnetic order. And going from here to here, you go through this quantum phase transition that takes you from this disordered state into this ordered state. And we can quantify this in different ways. So we can see that we really have a fair amount. When we do this, we really have a fair amount of occurrences of perfect order. This is in a 12 by 12 lattice where you really create this perfect checkerboard pattern. So you really are generating a long range order in the system, as far as long range as you can in these finite size systems. And you have pretty high fidelity, so you can kind of quantify the ground state probability and relate it to this fidelity where you get 0.97 per qubit for the entire sequence. And we can look further to the density correlations to quantify this long range order, and you see that the correlations are built up along the entire system essentially. Great, so we have this ability to kind of adiabatically go into this ordered state. And now I'm claiming that there's this Ising quantum phase transition here. Let's explore that. So as Trond mentioned, there's this kind of important Kibble-Zurek mechanism, which tells us essentially that as we go through a quantum phase transition, or actually as you go through a regular phase transition as well, there's a relationship between the correlations you build up and how fast you're going through this phase transition. So if you go very quickly, the system does not have time to build up correlations. If you go very slowly, you can create correlations over longer and longer ranges. And it turns out that this also is related to a critical exponent of the phase transition, right? So we've explored this in our system. So you see that we have this very fast sweeps, almost quenches, where you create short-range correlations. And in the very slow sweeps, you create these longer-range correlations. And so the Kibble-Zurek theory tells us that these are related by this critical exponent, by a power law. And so we can see that we can really collapse all of these and extract this number for the critical exponent. And this number matches pretty well with theory. So we do think that we have really a handle of this on this quantum phase transition here. Now, this is not the end of the story. So we know that after you go through a quantum phase transition, you generate these correlations as predicted by the quantum Kibble-Zurek mechanism. But there's more happening, and these are called coarsening processes. And theory predicts that they should happen both as you're crossing the phase transition, but also as you go into the ordered phase, you arrive at the ordered phase, the coarsening processes should still happen. This is actually a pretty generic kind of process in nature. So if you just think of any system which has a second order phase transition, quantum or classical, you quench this phase transition, you now expect the system to start ordering itself. For instance, you have a classical magnet, you take the temperature, you bring it below the Curie temperature. You know that the system eventually needs to order. And then the question is, how does the system order? And it turns out that in these types of systems, and this is intimately related to this second-order phase transition, it happens with this interesting dynamical process called coarsening. And this process kind of looks like, so this should be some animation. All right. So what you're seeing here, if you manage to catch it, is that you start off with very small domains. And then these domains start growing and growing. And this is the coarsening aspect of this type of physics. So you get this progressive growth of long-range order. And it manifests in these universal self-similar dynamics. So evolving in time looks like zooming in. That's what this self-similarity means. And this was first realized by Lifshitz in his important work from 1962. There's an essential difference between these types of processes that happen in systems with second-order phase transition as opposed to the nucleation and expansion that you get in systems with first-order phase transitions. And this is a generic process in nature, so it's important for many, many different things, including creating iron, including the composition of minerals and rocks, including balsamic vinegar and oil in your salad dressing. So this is a really kind of important process, but we're more interested in, what does this look like in quantum systems, specifically in the kind of strongly correlated quantum systems that we have in our lab. And how does it relate to this quantum phase transition that we've already explored previously? And this is very much motivated by theory work with Ryan and David, which are also our collaborators in this project. And there's been a bunch of explorations of these types of physics in BEC condensates and now also in the Google machine. So our experiment is initially pretty simple. So we start off with this disordered phase that I described before. So you see that if you kind of take a snapshot, you see these kind of almost random positions of the Rydberg excitations. And you can convert this to a kind of like an antiferromagnetic picture. So look at the staggered magnetization, and you see something kind of messy. And now we're going to cross the quantum phase transition. And you see already that now you have a pretty different situation where you have these ordered domains. And one can look at the correlation function and see that it has some kind of finite correlation length. And now, after we've gone into the ordered phase, we now wait and see what happens. So we hold the system, and we see that the correlation length grows. So again, the correlation function kind of like expands. And you see that one of the two orders starts taking over the system. And which of the two orders is actually random between different snapshots. But the system tends towards a situation where one order is dominating the other. And we can quantify this by looking at extracting a correlation length. And we see that as we hold, the correlation length grows significantly. Now we can also look at it in a kind of a different way. So we can look at the k-space correlation function, the structure factor. And if you look at the structure factor at different times, you see that it can collapse. It collapses onto this single functional form. And so this is a kind of suggestive of the self-similarity that's predicted for coarsening processes. So now we see these two kind of basic ingredients. We see establishment of long-range order. And we see some data that is suggestive of self-similarity. And I say suggestive because this is not perfect. So we know that we have another length scale coming into play here, and we believe this is related to the finite size of the system. Right. So now we have these coarsening processes happening in our system, but we have a bunch of tools that we can use to try to understand more intimately what's going on. So due to the fact that we have this fully site-resolved readout, we can map out all the domains in every single shot. And we can then try to see what kind of processes are happening. So one thing's clear here is that you have this kind of one type of order dominating the other. And you can see this by looking at the average size of the largest domain. You see that it grows as a function of the whole time. And it grows at the expense of the second largest domain and other smaller domains. So the big domain is eating up its smaller ones. And this is exactly what you predict for coarsening physics. And you can look at the full distribution of domain sizes shown here. and see that you progressively get larger and larger domains as the system evolves. At the same time, you see this peak at very large, small domain sizes. This is related to the fact that you have energy conservation in the system, right? So this is a closed system, at least to some approximation. So if you can't really have just a single domain encapsulating the entire system, because that would be the ground state. So where did this energy go? So what you have, you have this large order, and in the sea of large order, you have very small domains or even single spin flips, which have to be there due to energy conservation. So you see this flow that goes towards large domains, towards low k vectors, and towards high k vectors at the same time. And we can look at this type of kind of like energy transfer more intimately. So in each snapshot, we can look at the classical part, the diagonal part of our Hamiltonian. And we can also look at it and compare the energy that's coming from the domain walls versus the energy in the bulk. And what you can see here, so if you look at the total energy, you see it's conserved over time, as you would expect. But you see that energy is kind of being transferred from these domain walls into the bulk. So the domain walls are kind of shrinking, if you will, and transferring these and generating these excitations within the bulk of this other order. Okay, so this is already pretty interesting. Let's see if we can take this one step further. And the way we're going to do that is by introducing a tool that's for us a new experimental tool, which is local control. So the idea here is that we have this array of atoms in our vacuum chamber. We can use the same techniques that we used to trap these atoms to apply light shifts to specific atoms. So we can apply like Z fields to specific atoms. Here's an example where we're generating this type of pattern. And we measure kind of the strength of these light shifts by doing a Ramsey interferometry measurement. And what you see here is that not only can we apply light shifts to specific atoms, we can control with very high accuracy, we can control how strong this light shift is, and we can vary this in a completely programmable way. So we can choose arbitrary weights. And here we're going to use this to prepare some specific domain patterns. So we can now generate one order in a sea of the other order. And that's going to be important because this kind of tool allows us to follow the dynamics of domains. Previously, we're just going through the quantum phase transition to generate some arbitrary pattern of domains. And then if you want to look at how these domains evolve over time, you can't compare different snapshots at different times to each other. So now we can really follow the dynamics of the domain. And what we see here is that for this type of square domain, something kind of, it evolves pretty dramatically, it kind of like goes away, right? So you can imagine that it maybe kind of like melts, but actually it turns out that what happens is that it shrinks. And you can really kind of see this. So you can look at two different layers. One is a more outer layer of this domain, and then a more inner layer. And you see that first dynamics happens in the outer layer, and then after some time, dynamics starts happening in this inner layer. So you see that the domain walls really progress inwards. And that's an expression of the fact that this external order, the C, is kind of eating up the smaller domain in the center. And now we can try to probe the type of processes that control this evolution. And we expect this to be curvature-driven dynamics. So you see here that we prepare this zigzag-type domain wall, and we watch it evolve. And what happens is that it kind of like smushes to a straight line. And this is because the type of physics that's dominating here is surface tension type physics. So we have, and so we have the curvature of the domain determining its velocity. And we can look at this, we can quantify this. We can look at these points of high local curvature and these points of low local curvature, and you see that these points kind of evolve pretty dramatically, while points of low curvature almost do not evolve at all. Now, this curvature-driven dynamics also gives us some prediction for what happens to this square domain. So essentially, because the rate of we expect the rate of change of the radius or of the curvature here to be proportional to the local curvature, that means that the change in area has to be constant in time. So we can look at this, and we see that the rate of change, the rate of change of the area is indeed constant in time. And moreover, if we go the further away we are from the phase transition, the slower the dynamics happen, right? So if you're, these different colors are different distances from the quantum phase transition. If you're very far away, you get a very slow kind of shrinking of this central domain, and this accelerates as you go near the phase transition. And if we put these points against each other, you really see this kind of interesting behavior. And this is kind of an important observation. So what we have here, we have acceleration of the coarsening dynamics near the quantum phase transition, going towards the quantum phase transition. And this is actually a uniquely quantum signature. So what you would expect for the classical case going towards the thermal phase transition is that the dynamics would actually slow down rather than speed up. This is a signature of kind of this kind of uniquely quantum nature of the coarsening process happening here. And moreover, the rate at which you expect it to accelerate is related again to the same critical exponent that we discussed previously, this 0.62 or 0.63. And we see that it's at least roughly consistent with this type of behavior. And so now we've seen these coarsening processes happen. We have kind of understood some of the underlying processes and how criticality affects this. And we were trying to kind of understand this criticality aspect further. And when we went very close to the phase transition, something really interesting happened. So we saw that instead of seeing coarsening dynamics, what we're seeing is actually oscillations, if you can make it out, oscillations of these domains. So the domains were fully oscillating order. So they were flipping order completely, which is not something you expect for coarsening dynamics. And you can really see that these, this is pretty robust. So it happens along at various different points, going from the disordered phase, so on one side of the phase transition, to the ordered phase on the other side of the phase transition. And moreover, these oscillations are extremely dramatic. So the order parameter goes from -1 to 1, and you're seeing kind of oscillations which are in unity scale. So you're seeing very, very strong, very kind of aggressive oscillations of the entire system. So the entire magnet is oscillating. So we were kind of like puzzled about, what this is. And we're, for quite a while we were thinking, oh, these are like quantum scars. So quantum scars are these very interesting dynamical phenomena where you have, if you have the right combination of an initial state and the Hamiltonian, then these initial states do not thermalize or do not thermalize quickly. They undergo some really interesting evolution, which manifests usually in these strong oscillations. And so we're seeing these kind of like strong oscillations here, and we're thinking, this is the same system. So, okay, we probably have some kind of, quantum scars. But it quickly turned out that we were wrong. This is not quantum scars. And the way we understood this there's various different types of evidence that one can use to show this. But our first kind of like clue was, we had some theorists doing numerics, and we saw that, the type of states that we were preparing, which coincided, very well with our experimental measurements in various different aspects, we were preparing actually pretty low energy states. So this is the type of energies we were expecting to prepare. You can kind of compare this with the calculated gap in red here. However, the states that usually seed scars are these Z2 type states, and they're like much, much higher in energy, as you see here. So this kind of led us to believe that the differences between these two in energies kind of suggest that we don't have scars. So this is what we're seeing here. Is we're seeing very strong oscillations, but this is a low energy phenomenon. And moreover, what you can see here, another clue, is that the oscillations are centered around 0 in the disordered phase, but as you go through the phase transition, the oscillations start oscillating around some finite value of the order parameter. And this lends us to believe that this could be described by this Landau theory picture, at least on a kind of like a very kind of like 0th order approximation level, where you can think of the dynamics of the order parameter as being under this classical anharmonic oscillator. So the picture is that you have this type of quartic potential. In the disordered phase, this term is positive, so you have this type of potential, and the order parameter is just oscillating back and forth around 0. However, as you go through the phase transition, this Q goes to 0 and then becomes negative. And then you have this type of double well potential, and the oscillations will be around the minimum of this potential. It's a finite value of the order parameter. And so now we can kind of look at the oscillation frequencies, and what we see here is that the oscillation frequencies go down towards the where we believe the phase transition is, and then go back up. And moreover, they coincide pretty well with numerics for the ground state energy gap. So what we're seeing here is really this kind of like oscillations which are related to this really low energy structure. And we're almost kind of like measuring the many-body gap here directly. And what you see here, you see these other purple points. So these are the oscillation frequencies of the correlation length as it grows in the ordered phase. Am I doing on time?
20 minutes.
Okay. So you see these strong oscillations on top of this coarsening growth. And this is actually related to the same physics. And so in the ordered phase, when these oscillations are, if we go back a bit, in the ordered phase, when these oscillations are around the finite order of the finite value of the order parameter, this is analogous to what's called the Higgs mode, right? Where you have this vacuum expectation value, in particle physics language. Essentially, you have this kind of mode, these oscillations around the value of the order parameter, which is non-zero. And we see this also in these, on top of these coarsening physics. So we have both coarsening dynamics and this type of Higgs mode behavior happening simultaneously. And what's also interesting is that you have also these damping type physics. So if we go back and look at the oscillations directly, you can kind of make out that initially, if you go far away from the phase transition, you have these oscillations which are higher in frequency, but also don't decay as quickly. But as you go near the phase transition in darker colors, you have this strong decay of the oscillations. And this is kind of pretty interesting behavior. So you really see this peak in the damping of the oscillations near the quantum phase transition. And while the gap frequencies we can extract pretty well with these MPAs type calculations, the damping turns out to be much harder to extract. So you really have kind of like a pretty complex dynamics very near the quantum phase transition, which involve highly entangled states of the many-body system. And one can probe this further. So here are 2 points. One is far from the phase transition in the disordered phase, and one is very close to the phase transition in the disorder, very close to the phase transition, so almost on the phase transition. And what you see here is that as one increases the amplitude of the initial value of the order parameter, so we start off with a highly biased state, we get these strong oscillations. If we bias not as strongly, we get these kind of like smaller oscillations, which makes sense. But also, it looks like the frequency is also related to the amplitude. And this is to be expected in this picture where you have this quartic potential. In this type of anharmonic oscillator, the frequency of oscillations is related to their amplitude. But what's more interesting is as you go to the quantum phase transition, you see this much, much more strongly. So now, previously you were oscillating in this type of quadratic plus quartic potential. Near the phase transition, you almost have no quadratic part. You only have quartic part. So the potential is much softer. So for the same initial kind of value of the order parameter, you get much, much larger oscillations. And you can see this here. So here, the amplitude of the oscillations goes up to 0.6 as opposed to 0.15. And the sensitivity to the initial value is also much, much larger. So the relationship between amplitude and frequency is much stronger here. So we can also try to probe other properties of the phase transition here. So it turns out that there's, apart from the critical exponent that I described previously, there are many other universal properties of the phase transition. And now we have this type of pretty interesting type of probe into the phase transition with this Higgs mode evolution. And what you can see here is that, okay, so sorry. So one of the kind of other universal properties is the relationship between frequencies on the two sides of the quantum phase transition. So if we compare the frequencies on the disordered side and on the ordered side, you have some ratio, and it turns out this is universal, so it's unrelated to the specifics of the system. Now, if we go back to this, we look again at this, Landau potential, you can work out that the ratio between the frequencies, let's actually look back at these two. So the relationship between these frequencies has to be square root 2 if it's just this quartic potential, and this mean field predicts everything. But it turns out this is not the case. As you go to the quantum phase transition, this kind of simplistic picture fails, and you get a kind of really important contribution from fluctuations of the system. Right, and so now we can compare this. So instead of, we can look at the kind of the bare measurements are in red and blue. So you see here, the red is the ordered side, and the blue is the disordered side. And we can kind of try to compare the ratio between them. So the orange is comparison to square root 2, and the green is comparison to this other value, which is higher. And actually, this other value coincides with several calculations that people have done for this Wilson-Fisher fixed point, which is a fixed point that's related to this 2 + 1d quantum phase transition. And you see that the ratio here is kind of like more suggestive of this 1.9. Now, we're not really claiming that we've measured this 1.9 because this data set is kind of like not robust enough to actually allow us to fully extract the number. But the point here that I'm trying to make is that we have this kind of probe into kind of very interesting aspects of the quantum phase transition, which are not easily kind of accessible in other platforms. So to summarize, we measured these collective low-energy dynamical processes in a strongly correlated quantum system. So this is a system that's really beyond mean field, is strongly interacting, but we still managed to measure these type of kind of like very fundamental dynamics that happens as one crosses a quantum phase transition. And we observe this coarsening, this really kind of obvious growth of the correlation length beyond what Kibble-Zurich would expect. And we know that we've seen that coarsening is strongly affected by the criticality of the quantum phase transition. So we see that it speeds up as one goes near the quantum phase transition. And we're using local control. We were able to look at the dynamics of domain walls and understand how they underlie the process of coarsening. And finally, we measure these strong oscillations of the order parameters in these Higgs oscillations. And these give us kind of a very interesting and unique probe into the quantum phase transition. So we can measure kind of universal properties of the quantum phase transition using this tool, and also to some extent the many-body gap. Yeah, and kind of there's several different directions that we can think about taking this. So I've mentioned that we have the coarsening processes, so the growth of the correlation length, and on top of it we have this type of amplitude or Higgs mode. Well, this is the relationship between these two, and kind of any kind of interplay they may have is something that we're not really sure how it works. So we're not really sure like what's the full theory behind this, and it's kind of an interesting thing to maybe think about, if you're interested. So now we know we have this kind of unique microscope into the quantum phase transition. So there's many different universal aspects of the phase transition that one can think of exploring. And also just generally thinking of dynamics near the quantum phase transition is kind of interesting. It's related to a lot of very important kind of like physics that people are thinking about now. And also it's, we kind of know that it's very difficult to simulate numerically, which makes it more difficult to explore, but also possibly more interesting. And one can kind of take the same tools that we've described here and go beyond coarsening to look at other types of thermalization processes. Specifically, I mentioned that coarsening is intimately related to the second-order phase transition. And as you go through first-order phase transitions, you more kind of like typically expect this like nucleation and expansion. And this is related to what's in quantum mechanics called this false vacuum decay. So if you have you can prepare kind of like a metastable state, so supercooled water, for instance. And in classical systems, a small defect will seed the growth of this ordered phase. And this will happen, typically ballistically, and this has all kinds of interesting dynamical properties. In quantum mechanics, the seeding process for this thermalization process can actually be a higher order tunneling event. And actually, our universe is predicted to be in a false vacuum, according to some particle physicists. So actually, we could be subject to this type of fate. But there's all kinds of interesting dynamical questions that one can ask about these that could be explored using these similar tools that we've shown here. So this work was done by the atom array team at Harvard, supervised by Misha and co-supervised by Vladan and Marcus. And the theory work here was extremely important. So we had theory support from on the PI side from David and Subir, and Ryan and David came up with this framework for understanding quantum coarsening. And we had the support of these other fantastic theorists thinking about both coarsening processes and these types of Higgs oscillations that we really had to nail down. In our team, we're working also a variety of different projects, which I will not discuss today. But if you want to kind of like know about them, feel free to ask me about them. These include some projects we're working on in a quantum error correction front. We're now also working on doing some digital simulation of specifically of the honeycomb Kitaev model, generating some topological states of matter, using this new technique where we kind of do a Fluctuations engineering of doing sequential movements in gates. And finally, another type of kind of like Hamiltonian engineering that we're doing is this many-body Fluctuations engineering, where we're reversing the time of the many-body evolution and using that to generate interesting Hamiltonians. Right. So with that, I'll leave you and let me know if there are any questions.
Any questions?
How many hours of measurement did it take to get the final result? I think the bullet point of results, the last one, the latest results. The Higgs oscillations.
The Higgs oscillations, actually, so this is kind of a funny story. The Higgs oscillations, so the entire data set was a data set that we didn't even know we were taking at the time. So we were seeing these oscillations, and we thought initially, this is some kind of experimental, bullshit. And we were trying to kind of like scan just everything to figure out what was going on. And at the time, we also scanned, we did so many scans, and we also scanned the distance to the quantum phase transition and these different, so if we look at these oscillations, we were taking this data just to kind of like quantify what happens at different, detunings, and also this other data where I was showing where we're looking at what happens if you kind of bias the order parameter more strongly. And during all this, we had no idea what was going on. So essentially, like the main data set that I was discussing, like this one, this was, I think, like probably half an hour of measurements where we weren't even like kind of like focusing on kind of extracting this type of physics. And then when we started doing kind of like the theory analysis and looking at the data more kind of like closely, we kind of figured out this was going on. And actually, this data set was, pretty telling. Yeah. So this is like not a lot of data at all. Yeah. And actually, one can do an important point is that now that we know what's going on, there's a lot more that we can do beyond what was done here.
Yeah, hey, thanks a lot. I was wondering, so whenever you cross a phase transition, or I guess whenever you make adiabatic state preparation where you then have a gap, you would expect such oscillations, right? Because you would prepare a superposition between the ground state and the first excited state if you're doing relatively well. So I'm wondering, what is really the signature that kind of makes you identify that this is really has something to do with Higgs rather than saying, it's something more generic that you would always see even in the absence of that?
Yeah, that's, I think, a good question. I think so. There are kind of like theoretical subtleties as to what you would call a Higgs mode and what you would not call a Higgs mode. which we kind of discussed internally. And also, if people feel like, oh, you don't want to call this the Higgs mode, they want to call this an order parameter oscillation, I'm also fine with that. Well, I think the fact that like what happens in this, so we know that, in the types of sweeps that we were doing, really only at the only at the kind of like only at very small systems you would actually have a situation where you're really just looking at too many body states or a few many body states actually. And these types of systems, 16 by 16 systems with hundreds of atoms, we're definitely not looking only at like 2 levels. So we are probing kind of gap-related physics, but there's a bunch of excited states taking kind of like working in this, right? So I don't know if this is enough to kind of convince you that this is what you should call a Higgs mode. And again, there's all kind of subtleties related to that, but it kind of there's a lot of evidence that, for instance, here that this kind of fits pretty neatly, at least to first order with this type of Landau picture, right? So you really see that the behavior in many, many different aspects corresponds to what you expect from this like quartic potential. So it's kind of, I think, has more explanatory power, I would say, to think of it in this way rather than think of it as, oh, there's just this like gap. I also think that like only measuring the many-body gap is actually also extremely cool. And this is a pretty unique way, I think, to measure the many-body gap directly. If it is, to the extent that you can really isolate these like two levels on the low energy range. But nevertheless, yeah, we felt in the end that this is a more, a favorable way of framing it.
Okay, thanks.
Maybe a follow-up to that. I guess I'm a bit confused. Like, how well can theory model in terms of quantitatively like features of these oscillations? And you kind of mentioned that they have a decay rate that somehow is kind of intrinsically quantum. I guess so. Basically, the question is like, if there's a theory model and the calculation doesn't agree with the measurement, like to what extent can you attribute like the discrepancy to like whatever like imperfections in the system, or like to what extent is like the theory is not accurate, like the computation is not accurate enough?
Yeah, that's I think a very valid question and something that we asked ourselves as well. So I would say that so we definitely don't fully know everything that's going on in this point, right? So we know that our models capture the gap pretty well. As you go toward the quantum phase transition and you have more and more energy levels coming into play, it becomes harder to simulate numerically. And one can definitely make the case that there are other things happening beyond what we would kind of like naively expect here. So there's some other experimental process coming into play. What we do have is we have evidence all around here, on both sides coming towards the quantum phase transition. And we also know and believe that the dynamics are coherent, as shown from a variety of different evidence in essentially all of these experiments. So there's no good reason to believe the dynamics is not coherent only here or something like that. That would be kind of like pretty conspiratorial. But there could be other effects coming into play for sure. And we would definitely be interested in exploring this region more.
How prevalent is atom loss, and what do you do with shots with atom loss?
That's a great question. So kind of like the full answer is kind of like multi-layered. But okay, so first off, you do this kind of rearrangement step, and then you image the atoms before you do any kind of like a coherent evolution. So if the rearrangement is imperfect, you can post-select on that very easily, and we do to some extent. So kind of we see that if you have a small amount of defects, it doesn't seem like that there's a very dramatic effect on the dynamics. And then you can ask, what happens if you have atom loss during the coherent evolution? Well, if you have the typical type of atom loss that you have from kind of like benign processes, and I'll explain what I mean soon, that's something that we just live with, right? So there's some finite probability that the atom is lost within this time. It's not very high. And we've seen this, for instance, with this 0.97 fidelity per atom in this previous experiment. So we know that that's not kind of like a super major concern, but it exists, right? And there's and you in principle could also have detection error and stuff like that. What's kind of like less benign is that we now know that there are other types of processes which are kind of completely unrelated to the Hamiltonian that we want to realize in the system. And these are in the parlance of the field called sometimes like avalanche effects. So we see sometimes these highly correlated loss events where instead of having something that looks like a, kind of like a checkerboard pattern, like an antiferromagnetic order, you see just like chunks of the array missing, like large chunks of the array missing. And if we believe that the dynamics is just realized by this like Hamiltonian evolution, this would be like a super high energy state because there's like a lot of blockade violations. So what we know is that whatever is generating these types of outcomes is not the type of Hamiltonian that we want to do. So we kind of are post-selecting away on that. Yeah, so that's what we can do. We can like post-select away events which are obviously wrong, but we can't post-select away events which we don't know if they're related to actual physics or some noise.
Wait, so help me understand, because I heard that there was two types of events, right? Events during the state preparation phase and during evolution.
Yeah.
So during state preparation, I thought that those are immaterial because you would just rearrange your atoms to deal with it, right? Or is that not accurate?
So in principle, you could. We only do 2 rounds of rearrangement. It's just kind of like a practical decision as to how much you want to rearrange. And so what happens is that if after 2 rounds of these rearrangement procedures, you have too many defects, you just throw away the shot.
Okay.
Yeah.
And then the second question is then, so you were saying that if you have a benign loss, you can still incorporate that data, but that seems quite surprising, right? Because that Hamiltonian is fundamentally like there's a defect at that site, right?
Yeah.
Like,
So what I was saying is that I was saying 2 things. One is that for rearrangement post-selection, we post-select not only on cases in which there are no defects, but also in cases in which there are a few defects, because we see that that's not really kind of like doesn't make a dramatic difference in this like 256 atom array. So that's one part. Another part is that during the coherent evolution, you have further loss that you can't post-select for. And what I'm saying is that this loss is just small. There's not a lot of it.
and that's a function of it just being in free evolution versus doing like movement, right? Because atom loss primarily happens during movement, or is that not accurate?
Well, it can happen for a variety of reasons. Here, it mostly happens because your atoms are in this Rydberg state, and that's sensitive to all kinds of stuff that can happen. But essentially, during the coherent evolution, then this type of benign atom loss is pretty small.
All right, any other questions? If not, then let's thank Tom again.